Alrighty, my name is Ryan Hertline, and for today's video I'll be walking through the derivation for the matrix vector equation for linear regression. Alrighty, let's see if this angle works. Alrighty, so we'll start out the derivation with an arbitrary vector, and we'll call that v. And this will just be in 2 dimensions. Can we see that? Yeah, we can see that. Alrighty. So we're going to try to approximate this vector v with some sort of basis vector, and we'll call that u. So let's say our basis vector is kind of more flat, more on the x-axis, and it's a short little basis vector, so a unit vector in this case, and we'll call that u. Now, right off the bat, we'll see that we're only going to be able to get so good of an approximation of this vector v with this base vector because they are not lined up with each other. They're not in the same direction, and they're also not the same magnitude. But we can get as good of an estimation as we can by multiplying this basis vector u by some constant. So I'll write out 3 more of these. So this is now 3 of our basis vector u. And that is about as good as we can get with these base vectors going in this direction. Now the error term is going to be the vector between the end of those base vectors and then our vector v. So here's another vector, we'll call that e for error. So in this example, again, we are approximating our vector v with some constant c times our basis vector u. So that's what this looks like here. Now, we can say that our vector, instead of just being approximated by, our vector is actually equal to c times our basis vector u plus that error term, that error vector e bar. Now, again, this is the best possible approximation of that vector v that we're going to be able to get. And the reason we know that is because this vector, this error vector, is perpendicular to these basis vectors going in this direction, or orthogonal. So in this case, if we were to subtract 1, the angle between these base vectors and that error vector would be greater than 90 degrees. And if we added another one, it would also be greater than 90 degrees, and that error would increase in length. So again, the best approximation of this vector v with these basis vectors u is when this error is at a 90-degree angle, or perpendicular, in this case orthogonal, or in a more general sense orthogonal to these basis vectors. So what this means is that we can rewrite this saying that the error vector e bar dot product u bar, which is our basis vector, is equal to 0. And the reason we use the dot product in this case is because the dot product is equal to 0 when those vectors are orthogonal to each other or perpendicular. Now we can rewrite this dot product a couple different ways. So I will draw 2 new vectors just kind of in a random direction, a on top and b on bottom. And the dot product of a and b is equal to the magnitude of those vectors times the cosine of that angle that they make in between each other, theta. So that when they are perpendicular, theta is 90 degrees and cosine is 0. So that's what we're looking for in this case for our best approximation of that vector v. Now we can write this dot product in a couple of different ways. So this is the first way. Another way that we can write this dot product is actually by doing a component-wise multiplication and then addition of the components of these vectors. So let's assume that these vectors are in 3 dimensions, or three components. So we'll do a1 b1 plus a2 b2 plus a3 b3, and we could take this all the way out to as many elements as those vectors have, and we can write this as a summation from I equals 1 to n of a n bn, and that'll come in handy a little bit later. Now the third way that we could do this is with a transpose notation. So we can do a transpose b, and the commutative property applies here, so we could flip this also. So we've got B bar transpose A. And that'll come into play a little bit later as well. Now going back to this example over here, we can rewrite this error term as vector v, our original vector that we're trying to estimate, minus the constant times our basis vector u prime. Now what we can do additionally here, taking this a step further, we can substitute this into this dot product, getting this to 0 for the orthogonal relationship between the error and our basis vector. We could say v bar minus c u bar, all of that dot product to u bar equals 0. Now we'll stop here in this example and we'll take this into 3 dimensions. So I'll draw new axes and a new vector down here. So we'll do x. Let's see, how do I do? Okay, so x, yeah, that's x, and then that's y, and then z. Alrighty, we can see that. Yes, we can. All right, so I'll switch to a new color. Let me adjust this light. There we go. Okay, so switch to a new color, red, just to help with this illustration. But we'll draw a new vector here. Call that v again. And we'll say that this is in the y plane, or the zx plane. So I'll drop, actually won't do that yet. So this is the vector that we're trying to approximate. Now in this case, because we're in 3 dimensions, we're going to have 2, so we'll do two basis vectors, and we'll call these phi 1 and phi 2 instead of u. So I'll draw these there and there. So that's phi 1 and that's phi 2. Alrighty. Now, these basis vectors form a plane, just because any 2 vectors in a 3-dimensional space or above create a plane. So we'll kind of draw that out here, like this. Now, if we're using phi 1 and phi 2, draw more bars. If we're using phi 1 and phi 2 to approximate our 3-dimensional vector v in this 3-dimensional space, the same principle as above applies. So we need this vector v, or we need that error term actually, to be perpendicular to both phi 1 and phi 2. So if you're thinking about this in 3 dimensions, our approximation is going to be in the 2-dimensional plane that is formed by those basis vectors phi 1 and phi 2, and we want that error term to be orthogonal to that plane, so perpendicular to both axes of that plane, in this case phi 1 and phi 2. So we can draw this out the same way. So we'll start with, let's see how we're going to fit this. This will work just fine. So we'll start with, again, we're approximating vector v as a linear combination of these basis vectors phi 1 and phi 2. So c1 phi 1 plus c2 phi 2. Now that is going to be equal to c1 phi 1 plus c2 phi 2 plus our error term, plus our error term. So that's equals instead of approximated by, and I need to add those hats here as well. Alrighty, so that's what we've got so far. Now let's go back to this, and again, we need the error vector to be perpendicular to both of these basis vectors, phi 1 and phi 2, so we can rewrite this the same way. First, let's solve for the error. So we've got error equals v minus c1 phi 1 plus c2 phi 2. And we're going to need to write both of those statements. Error is dot product phi 1 equals 0, and error dot product phi 2 equals 0. Both of those statements need to be true for this to be the linear combination of our basis vectors phi 1 and phi 2 to be the best possible approximation of that vector v. Water bottle. There we go. Now we can sub this into these equations just like we did up here, but we're just going to start with phi 1, and we'll eventually expand this because this works in any number of dimensions, not just 2 or 3, but we'll start with phi 1. So again, error vector, dot product, basis vector, not u, but we're going to do phi instead. Oopsie, oopsie, oopsie. phi1 has to equal 0, and that error vector is equal to v minus c1 phi1 plus c2 phi2. Now again, let's sub in this expression for error into this term here. So we're going to v minus c1 phi1 bar plus c2 phi2 bar. All of that dot product to phi1 is equal to 0. Now the distributive property works with these dot products as well. So we can think of this dot product being applied independently to our vector here, our main vector that we're trying to approximate, and then also this linear combination of our basis vectors phi1 and phi2. Now again, this can be extrapolated for any number of dimensions, but here we're just focusing on 2. So the next step is going to be carrying out that distributive property, and then I'll bring the vector times the phi1 basis vector over to the right. So I'll rewrite this as c1 phi1 bar plus c2 phi2 bar dot product phi1 equals phi1 dot product v vector. Now at this point we'll revisit those different ways of drawing the dot product, and here we'll use the transpose. So instead of vector 1 dot product vector 2, you can take either of those and transpose it, meaning that instead of say like a column by, so instead of like a column vector, it then becomes a row vector, so you flip it like 90 degrees. Now for this, we'll assume that these are all column vectors, so when we transpose one of these vectors, it will become a row vector. So we will instead rewrite this, and I'll do that distributive property once more with this phi1 vector over here. So I'll do phi1 transpose c1 phi1 plus phi1 transpose c2 phi2 equals phi1 transpose v vector here. So this is what this now looks like. I'm just trying to make sure I'm not in the way here. I think this works. Great. So our next step is going to be to think of this in terms of what these vectors actually look like on the piece of paper and how many dimensions these are. So what we're getting towards here is linear regression, and a common example of how to apply that is to develop a model for data. So let's say here that our data, or our vector v here, is going to have 100 data points in it. So I'll rewrite vector v over here as, again, a column vector of data points. Say we're taking people's temperatures. So one person's might be 98, 98.6, 99 if they have a fever, 97 if they're a little bit cold, yada, 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 all the way down. We've got 100 of these. So this is going to be a 1 by 100 vector. Is that right? Row times column. No, 100 by 2, excuse me. This is going to be 100 by 2 by 2 vector. So in this case, we are approximating this in 2 dimensions. And we've got 100 here, like this. So actually, we would have x's over here and y's over here. Say, this example doesn't exactly work for that. Let's say we're trying to approximate something instead of temperatures. Let's say we're gonna do like a linear graph. So we've got y equals some function of x. So we've got x's and y's going down like that. So from here, we're going to rewrite this in terms of what those vectors actually look like. And we're going to take this vector here, which is our phi1 transpose, and instead of we'll start with the constants and then our phi1 and phi2. So we'll group together phi1. We'll group together phi1, phi2. And then we'll bring together C1 and C2 over here, matrix multiplied together because we have column times row and then column times row. So this will result in C1 phi1 times C2 phi2. And then we've got this transpose over here. So instead of a column vector like it is over here, we're going to flip it 90 degrees. So it's going to be one big row. So we'll have phi1 going like this. Now over here on the right, we're going to have the very same thing. And we are going to have that transpose first, phi1, times our vector v, which is going to be like this. There we go. Now this is actually a single set of points. This is going to be 1 by 100 vector. We've got 100 data points in that vector v. Now again, this was only for one of those basis vectors, phi1. Now in this example over here, we have 2 dimensions, or two basis vectors that we're going to be approximating that vector v with, so phi1 and phi2. So you would rewrite all of this for phi2, the other basis vector. However, this would result in something that looks very similar, and we can actually combine those. So we'll bring phi2 over this way, and then phi2 over this way. We can kind of stack these. So then this becomes, instead of a 100 times 1, or instead of a 1 by 100 vector, this is now a 2 by 100 vector. This vector here becomes our design matrix. So I've been saying vector instead of matrix this whole time. So this is a 2 by 100 matrix, not a vector. This becomes our design matrix, which is going to be the other way around. So this is 100 by 2. And then this is a 2 by 1 for those constants, C1 and C2. Equals over here, same thing, that phi1 transpose, phi1 and phi2 transpose, those basis vectors, 2 by 100. And then this is a 100 by 1 vector. Now here we've taken a complicated set of math if you were to do each of these individually, and using the vector matrix form, we've turned this into a more simple problem, because when you multiply these together, switch these, you have a 2 by 2 matrix times those constants, C1, C2. Results, when you do the matrix multiplication over here, you've got a 2 by 1 matrix again. So we have 2 unknowns and 2 equations for those unknowns, meaning we can solve for C1 and C2, which will give us the best approximation of that vector v that we were approximating as a linear combination of those basis vectors phi1 and phi2. Now again, this can be repeated for any number of dimensions. You will just stack those basis vectors this way, stack your design matrix, that's what this one is called, as actually written as, we'll call that A, with 2 bars over it, so design matrix. And this can be, again, repeated for any number of dimensions. So yeah, this was the derivation for the vector matrix form of the equation for linear regression. Thank you.